Okay, good afternoon. I'm Wes Hines. I'm the Nuclear Engineering Department here at the University of Tennessee. Welcome to our Colloquium series. Today we're very lucky to have one of our own. Dr. Luke Qualls got all of his degrees. You don't have any other degrees. I know you have 3 degrees from here, but you didn't get any from anywhere else, did you, Lou? Okay, so bachelor's, master's, PhD, back in the Pasqua era. There's some great stories about the time when Dr. Pasqua ran the department. Anyway, he's the National Technical Director for Molten Salt Reactors for the U.S. Department of Energy's Office of Nuclear Energy, and also serves as the Reactor Technology Integration Lead for Oak Ridge National Laboratory Reactor and Nuclear Systems Division. In these roles, he works with the DOE to support industry efforts to develop and deploy commercial molten salt reactors. He's been a researcher at Oak Ridge since 1988, working on a wide range of nuclear projects, including fusion energy, nuclear space power systems, advanced fission reactor concepts. Welcome, Lou.
Honor to be here. I appreciate the invitation. So yes, I'm Lou. If you're working on it, I've probably worked on it too. So you're free to ask questions about just about anything. But today we're going to talk mostly about molten salt reactors. A little bit of history. Unbeknownst to me, my career started on March 28, 1979. Anybody know what that date was? 3 Mile Island accident occurred on that date. Okay, I was a junior in high school. Okay, had no idea. I grew up in West Tennessee, and there's a fault line that runs right down the western Tennessee boundary. So there's no nuclear power anywhere near where I grew up. So it was just never a topic. Okay, so 3 Mile Island was a big news story. Followed it a little bit on the news, and by the time I got to college in fall of 1981, the topic had died down considerably, and I didn't hear any more about it. So first year here, I came here to study architecture and play lacrosse. Okay. After about a year of that, I had some promise as a lacrosse player, but absolutely none as an architect. The aesthetics of it just were lost on me. So, but I was kind of interested in how the building stood up. That seemed more interesting than what it looked like. And so I thought, well, maybe I'm an engineer. So in 1982, I decided to study engineering. And I went to the engineering department and said, I'd like to be an engineer. And they said, well, what kind? And I said, well, I don't know. So I went on the circuit. I went to all the engineering departments, and I would talk to the department heads, and I would say, hey, I'm interested in being a student in your department. And some of them expressed little interest in me. They had 3,000 students. They didn't need 3,001, right? Some of the departments I wasn't all that interested in. Electrical engineering wasn't my thing. So, but I walked through those doors. Let's see if this works. Right there. Okay. Pasqua, then it was just called the Nuclear Engineering Building. Went through those double doors, took a left, and then in that office to the right was Dr. Pasqua's office. And I remember sticking my head in and saying, I'd be interested in learning more about nuclear power. I don't know anything about it. And I'll never forget, he pushed everything aside. He sat back, kind of folded his hands, and I sat down and we talked for what seemed like a couple hours, a long time. And I remember walking out of those doors, and I go, boy, I still don't know much about nuclear engineering. But I know that in this building there is somebody who's going to care whether or not I'm successful. And I said, so that was the deciding factor. I felt like I had a home in the nuclear engineering building, in the nuclear community. Now it's full of quirky characters, I'll give you that. But it's a family. And so I remember going back out those doors and telling my roommate, who was from Harrisburg, Pennsylvania, I was going to be a nuclear engineer. And he knew a lot more about nuclear energy than I did. even though he was a wrestler and a history major, because he grew up in Harrisburg, and they talked about 3 Mile Island quite a bit. Anyway, so that was my start. And one of the things that Dr. Pasqua told me that really caught my interest, he talked about the energy density. He said you can burn wood for a little while, you can burn coal for a little while. He said, but nuclear power has the energy density that you need to power the future. Okay, so I was really intrigued by the idea of energy density. There are other good reasons to do nuclear power. Right now, low carbon electricity is a big topic. It was not a topic at all when I started the business, really. Right? National energy security is a bigger topic now than it was back in the day. Having a diverse energy portfolio is important. So nuclear fuel can be all of these things, and these are the important reasons why you want to continue developing it and deploying it here in the U.S. The real fascinating thing is just a few pebbles in a pebble bed reactor can produce all the energy you need for a year. Okay. The waste volume is low, energy density is high, it's a safe system, so we need to continue to pursue this. Now, a lot of people talk about low carbon electricity as the driving factor. It's certainly an important factor, but it's not the only factor. There are other reasons on their own merits to continue developing and deploying nuclear energy. That was the one that caught my eye. This is a picture of the reactor at Oak Ridge National Laboratory. This is the X-10 reactor, also known as the graphite reactor. This was the first reactor that was specifically built and continuously operated for a purpose. Okay? Its purpose was to irradiate uranium and create plutonium so that the chemical labs at Oak Ridge could separate the two. Okay? So this lab started operation in about 43 and ran to about 63. It was during this time where everybody was thinking about what you could do with nuclear reactors. This was just one example of how you could run one. This is a air-cooled reactor. You're tardy. No. This is an air-cooled reactor, and so what you see here, these guys have a long rod, and they're sticking fuel into a huge cube of graphite. And the graphite has holes drilled through it, and into those holes they're placing fuel. And within this big cube of graphite, there's this approximately spherical shape of fueled region, which is creating the chain reaction. And the air gets pulled into these front holes and through the holes and out the back to cool the fuel, cool the graphite, and protect these guys from getting particles coming in their direction. So it's quite safe to stand right there and load up this reactor. This reactor was about 4 megawatts by design, and this was one of the reactors where they proved out a lot of the theories of reactor physics. They made the first medical isotopes. They made the first plutonium that could be separated. So it was a workhorse, and it happened in the very early stages of nuclear power, and it ran from about 43 to 63, which is about the year I was born, 1963. So this was still running when I was first brought onto the scene. I always thought nuclear power was really old. I don't think that anymore because it's about my age. So this is a mixture. This shows the mixture of energy that's used in the U.S. since its founding back in the day, 1776. We didn't do much, and we burnt some wood for a while, and then we decided we could burn coal. Okay, and so coal powered us until the early 1900s, and it continues to do so. So one thing I want you to notice about this, when you have a product that replaces a product, it still takes a long time for one to die out and one to grow in. Okay? So you see this on these other technologies as well. We didn't start really driving cars until after 1900, and so the petroleum business started after that, and it ramped up. It took a while to build into the market. Okay? Here you also see natural gas comes in after petroleum comes in. And they started using it for heating, other purposes. And then about the time that the Oak Ridge reactor was ending its life, they were starting to get commercial nuclear onto the market. Okay, so from the 60s to the 70s, we had this expansion from nothing, bootstrapping from nothing, to having a mature reactor industry that had about 100 operating reactors in it at that time. And so you can see the mix that we had about 10 years ago, still heavily reliant on the fossil fuels. Petroleum still a third of our energy consumption in the world. Nuclear is building in, but it has saturated where it's at then, isn't it, where it's at today. And we have this right here, which is kind of an interesting mix. We decided we're going to, through policy, reduce the use of coal. That's great. But if we can't turn up any of these other options, we only have one knob to turn, and it's natural gas. And that's what you see. Natural gas consumption increases to compensate for the coal coming offline. Now, makes perfect sense. We have a nice broad energy mix, still very heavily reliant on fossil fuels. Whether you think that's a good idea or a bad idea, it's still a temporary idea. So if you want to look down the road a few hundred years, a few thousand years, you need to figure out how to solve those problems. And so your options end up being down here with nuclear, biomass, renewables, and hydroelectric. It's going to be a challenge to get much more hydroelectric. Okay. Renewable market is coming online and increasing, solar and wind, but they're not going to make a robust energy sector, at least in our neck of the woods. Biomass, yeah, we're burning more wood again than biomass. That's good, but it's limited, very low energy density. Our option is nuclear. Our option is nuclear. So, this is the projection of the current nuclear capacity in the southeast region, and it's plotted here as a function of the expiration date of their licenses. So you can see we're running along. We have about 30,000 megawatt equivalent plants in the southeast, and they're going to start coming offline, and by mid-century in the 2050s, all these licenses are going to be expired. Now you can shift this a little bit to the right by licensing extension, but you're still going to be facing this decline. Okay. So the question is, what is the nuclear business going to do to replace this coming reduction in its percentage of the market, and in fact increase its percentage of the market to compensate for the fossil fuel you want to get out? That's where advanced reactors come in. I work in an area of DOE and advanced reactor technology, and we're looking for what to do next. Now, what to do next can be a series of things. It can be build more light water reactors, build different light water reactors. Those are good things, and we should do those things. There's got to be something beyond those as well, because there's other things we need to take advantage of. One of the problems is, since 3 Mile Island and Chernobyl and these other events, the cost of nuclear power has gone up dramatically. So you can have a better technology, but if it costs so much more than anything else, it's still not going to get utilized. So an important thing is to maintain the safety that we have, improve it if you can, but improve the economics so that you reduce the financial risk of building reactors so people actually want to do it. So those are the challenges we have to. And we have about 20 years before these options need to be available and ready to go. So I like to show this slide. What you see here in the lower left is a propeller handmade by the Wright brothers, circa 1905. Okay. Built an airplane out of it. It's amazingly efficient, that propeller. They were geniuses with a high school education. They could do things you couldn't believe. But, you know, when we fly around, we don't fly on these anymore. We fly on these. Okay. So the evolution of technology in 100 years can go amazing places. Okay. And if we want our nuclear business to be successful into the future, we have got to increase the iterative process and build into our design the ability to improve and innovate these systems. So that's a big thing. So make them safe as they already are or better. Reduce the costs, learn from them, build next generation designs, and don't be all in on a solution that's going to last for 80 years because you won't have a chance to upgrade it along the way. So you need something different. Molten salt reactors are different, absolutely different. What you see here is a schematic of a simplified reactor. There's the reactor vessel, and inside that there's some structure that moderates fuel. The fuel is a liquid form that flows into the core, and Once it gets in the core, it becomes critical. It heats up. It comes out of the core, hits these pumps. These pumps send it through a heat exchanger, and it gets exchanged to a secondary system. So it's a very simple system. The basic features are a pot and a pump and a heat exchanger. And as long as your pumps are spinning, your reactor is running. So it can be a very highly reliable system. The other thing is your coolant material, your salt, is very low pressure. So you can have a very high temperature, increasing your efficiency, and a very low pressure, which means your components can be thin-walled components and not these very thick pressure vessels that are very expensive to build. So you might have a vessel thickness that is 1 inch to 1.25 inches wide. The cost of that's going to be very low. And if you can figure out how to replace it once in a while, then you can go in and upgrade it every few years. And you don't have to build something that you think is going to last for 60 or 70 years. It can decrease considerably the capital cost of these systems. In this particular configuration, the salt stays in this area until you want to drain it down to a drain tank. So if you have an emergency situation, you lose off-site power, you can drain your salt into this drain tank, which would be set up to take away the decay heat. Will allow the salt to solidify if you want without damage to the system. And then when you're ready, you can heat it back up and pump it back in and start all over again, start your reactor again. So this particular option has a drain tank, but a lot of companies are looking at designs that just have the vessel and they never drain it. All right. So molten salt reactors are really a broad class of reactors. There's two main categories. One is a solid fueled reactor concept that is cooled by liquid salt. Low pressure, high temperature coolant. Very good. So that's called the FHR because the salt's usually a fluoride-based salt. Dr. Brown and I worked on a few designs of FHRs that kind of started this concept going back again within DOE. It uses the pebble fuel or prismatic fuel, and the technology is pretty well known. It's the same salt that we used for the MSRE a long time ago. Pebbles can be made. Graphite's pretty well known. So this FHR is a concept that is potentially fairly near-term exercise. Okay? The other side is liquid salt-fueled reactors, where you actually fill up the reactor with salt, and then you start loading in salt that is uranium-based or plutonium-based salt until you have enough salt to create a critical configuration. So now your salt is circulating all throughout your primary system. And that's fundamentally different than what the regulators are looking at today, right? They expect their fuel to be in a cladding, in a bundle, in a very nice, well-known place, and never to melt. That's the goal. It never melts. And I say I'm pre-melt condition. Right? Our salt, we intend for it to be melted fuel, and we intend for it to be all throughout the primary system. So there's a lot of accident scenarios we don't have because we're already melted. We can't damage the fuel in the same way others can. But we have to deal with the fact that we have fuel distributed throughout the primary system. There's going to be a lot of radiation around this plant, and it's also not going to be under a few meters of water, which serves as wonderful shielding for the core and other designs. There's two versions, a chloride-based fast reactor system that doesn't have moderator in the core, and then the fluoride-based thermal system like the MSRE. They all derive pretty much from the molten salt reactor experiment that was done in Oak Ridge. And the business model is different for everybody in this game, but you need to make a product that somebody wants to buy ultimately. So high quality heat, electricity, you could argue you have increased resource utilization, you can produce medical isotopes and separate them out of the salt, and you want to potentially be able to reduce waste with these products. All improvements over what we do today. So this is a picture showing the molten salt reactor vessel, and some poor guy up here had to pose for a picture, but it's not very big. This core is, the internal structure is 52 inches tall and about that across. It's really compact. This was designed for 10 megawatts. Okay, and you can see in the molten salt reactor experiment, that vessel sits right there, and there's your pump, and there's your heat exchanger. So the theme of a pot and a pump and a heat exchanger are all contained within the central part of the facility, which has a containment barrier here and another one here. Drain tanks are down here. When you want to, you drain the salts out, put them in the drain tanks. When you're ready to go, pump them back up and start all over. In the MSRE, the control room was up here overlooking the bay, and there's a salt-to-air heat exchanger that the heat was just dumped up the stack. Very simple system with really one moving part, and that's your pump. This is a top view of the molten salt reactor experiment. This guy's not posing for a picture, he's doing real work. So he's prepping this up for its run. This is the top of the vessel here. You can see the pump here and the heat exchanger here, and it's inside that containment structure. This was operated and started running in about 1964. So you remember I told you the first reactor that was ever built for continuous operation, 43 to 63. During that time, they started with new reactor concepts that they thought they could build and experiment on. So in about 1950, they started talking about the molten salt reactor as the best reactor option. So Oak Ridge was a big advocate for this, and they pursued it from 1950, doing their background work. In the the early 60s, they decided they knew enough about one to build one, and in a couple years, they constructed this, and they started operations in 1964. And in this original run, they used U-235 as their fissile material. And if you notice, the cadence here is pretty slow. They loaded the salt into tanks, and then in January, they started moving the salt around. They had the first criticality about a half a year later, and then they had the first operation in the megawatt range another half year later, and then full power another half year. So they're learning about this system as they go, very cautiously checking on the operational capability of the pumps and the valves and the seals and all that, and then bringing it up in power slowly and running it. So they did an operational period, and then they stopped, and they decided to take out the U-235. So they drained the salt down to the tanks. They did a process to remove the uranium, and they put back in U-233. So this would allow demonstration of both U-235 and U-233 and paved the way for the thorium-uranium fuel cycle, which was a real push for this reactor design. But now look what they learned. From here, they had August, they loaded up the new fuel. October, they had first criticality. January, they were at full power. So the system was very well behaved. They understood it very well, and they were able to get it up and running again very quickly. And they only did these 2 runs. But in these 2 runs, they had a 6-month operational window where they ran continuously, which is remarkable for a first-of-kind reactor with a pump in it. Okay? So very successful operation. You can see the difference in this gas-cooled reactor, the air-cooled reactor, 4-megawatt design, very big. A liquid-cooled system can be much smaller, much higher power density, much lower cost. So I work for DOE, and we have an area of the program called the Advanced Reactor Technology Program. And our job is to develop advanced reactor technologies that can come online and supplement and support the light water reactor fleet and be the next generation reactor. And they look at many different types of reactors, but the main categories are gas-cooled reactor concepts, sodium fast reactor concepts, and the molten salt reactor concept. So molten salt reactor program was canceled back in early 70s because there just wasn't that much need or interest in it at the time. And DOE studied the sodium fast reactor quite extensively. And then later, after we had some reactor incidences, there was the push to look at the gas reactors because of their passive safety. But nobody was really working very much on molten salt reactors, except for a few researchers that were excited about it and enthused about it. And they kept the lights on. But industry started getting the idea about developing an advanced reactor based on molten salts. That sparked the DOE's interest in it. They sponsored some research that we worked on. And then ultimately, about 3 years ago, DOE said, let's establish a program to advocate for and do research for the molten salt reactor. And I lead that program, My job is to facilitate industry in the successful deployment of a commercial molten salt reactor. So I'm not here to build a government molten salt reactor that we can run as a test, but if I need to do that, I would do that. The purpose is to help a company mature a design to the point where it can be commercially tested and, if successful, deployed. So I spend a lot of time talking to a lot of people in a lot of places. Talk to industry partners who want to design these reactors, the DOE and the NRC who have to regulate them and want to understand them, national laboratories and universities where the research gets done. Okay? And it's very important that these three bodies be on the same page. Right? We have a short time frame to get to a commercial prototype. People need to understand why we think it's a good idea, what we're doing to make sure it's a good idea, and have agreement as we move forward that when we get to this point where we demonstrate it, there'll be a path for commercialization. So I spend a lot of time thinking about this iterative loop of design, evaluation, and testing. At the top of that loop, go around a couple times. We want to break out of that loop, build a reactor, and actually test it. That's the goal. So in a program like this, what do we generally need to address? Chemistry, physics, technology, and engineering. Is it technically viable? Does it make sense? What are the issues? Chemistry is a little different for a molten salt reactor because the salt is a chemistry experiment, and you're going to be putting fission products directly into the salt as you operate it, and so you're going to continually be changing the salt over time. You already have this distributed melted fuel around the plant, so you're going to have to understand what chemical species form and how those chemical species transport throughout the plant system. So chemistry is one of the number one topics that we work on. Physics, reactor physics of this, we know from experience the MSRE how it behaved. We have tools today that can calculate responses of reactor designs much better than back in the 60s. But we still need to develop the technology to put these systems together to test them to verify both our chemistry and our physics. Licensing. It's not going to do us any good to build a reactor technology that you can't license. So the regulator has to develop a framework that you can follow to license a reactor. So we spend a lot of time with the NRC understanding what they'll be needing and looking for, identifying gaps, doing research to close those gaps. Waste product. I don't think it's a good idea to talk about any next generation reactor concept if you don't have at least a pretty good story about what the waste is going to look like and where it's going to go. Okay? I think it's just the industry needs to take that on better than we have before. So we spend work talking about and characterizing waste forms that might come out of these reactor systems. It's salt, activated materials, graphite that may have some fission products stored in it. Non-proliferation. The nuclear business is an international business, and any product that you can build for this market, you'll want to sell in other markets because you got to sell more to make the money you need to make. So the idea is we hope to build them with U.S. companies and U.S. technology and export them around the world, but there are a lot of issues associated with handling special nuclear material and keeping up with things that would be of concern for proliferation. Right? I've got a salt that has distributed around the plant. I can sample that. I can take stuff out. I can put stuff in. How do I know that it's being done appropriately? What kind of safeguards do I need to build into the design so that a third a partnering country will let us build it there and we can run it reliably? Economics. It doesn't make sense to build it if it costs what current nuclear plants cost today in this country. We've got to cut those costs down to be competitive. We don't have to be below the lowest natural gas cost because these are historic lows. We have to be competitive. Maybe we cost a little more, but we bring a lot of other aspects to our energy economy that are valued and important. But we can't cost 3 times as much as other options. So risk mitigation is the name of the game. Look at all of these issues and decide what our biggest concerns are, prioritize our research, and try to drive them down. So this is the very busy flow graph that I put together to describe the problem, but I'm going to make it a little simpler. I want you to think of a cabin in the woods that has a wood stove in it. Right? The wood stove, you open it up, throw in some nice dry oak, start the fire. Right? You get particulates and smoke and vapors that come out and go out the chimney. You get ash that gets left behind and collects in the bottom. Right? So, where did everything go and what does it matter? Well, over time, you're going to run out of oak, you're going to throw in wet pine, right? And then you're going to have contaminants and corrosion. So that ash is going to rot out the bottom, and you're going to collect flammable material up in the wood, in the stove and the stack going out the building. And in 10 years, you might light that thing up and have a safety problem because you have a chimney fire, okay? So I think of the problem for molten salt reactors kind of on those same terms. I'm going to load up with a nice, fresh, clean salt, and I'm going to operate it for maybe decades. Okay, what am I putting in every day? What's it getting converted to? Where is it going? Can I account for that? And am I building up a potential issue that I didn't have on day one that I might have on year 10? And how do I convince a regulator that I don't have those problems? So this is a way to do what I call mass accountancy for molten salt reactors. First of all, you get the chemistry data that you need so that you know how the salt behaves. And then you take a reactor design and put that salt in that reactor design and do some reactor analysis and see how the reactor behaves. The designs would come from industry. Okay. Then as we run this reactor, we can do a depletion analysis, and then we can determine what the salt composition is. And if we've done our homework, we've got all the thermophysical and thermochemical properties in a database that we can use to help understand how that salt changed over time, how its properties changed over time, and how that impacted reactor behavior over time. So we do that cycle there. These chemistry models, we can also predict what species things are in, whether they're gaseous or liquid or particulates. And then from there, we can get transport models that tell us where they go. They're probably in one of these spaces. Volumes such as graphite that has porous structure. They're in the salt. They're on surfaces. They're in gas spaces, or they're off to the off-gas system. So me trying to figure out what's in the salt that matters, and what matters is, does it influence reactor behavior? Is it a significant contributor to dose around the plant? Is it a significant contributor to dose consequence in a potential accident scenario? Those are the only things I really am looking at the moment. Okay. Other things will matter. If you have uranium that is precipitating somewhere in the system, you might be forming a solid mass. Could that be a criticality concern? You better know that as well. Anyway, so following these things is a big part of the licensing issue. Understanding how the reactor is going to behave is directly related to salt composition and behavior. So you have to solve all these problems kind of simultaneously. So we talked a little bit about transport. Tritium is an example of a product that is of interest because the thermal flibe-cooled reactor concepts will make a lot of tritium. So you can only release so much to the environment. You can only release so much into your containment spaces. So you're going to have to understand how it forms, how it speciates, how it transports, where it's going to end up, so you can design mitigation systems around that. So that's one of our challenge problems, understanding the tritium transport.
Tritium comes from the lithium and the fly.
Yes.
Why do we choose lithium?
So when they looked at these salt mixtures back in the day, they were balancing two things, the neutronics of the core and the thermal hydraulics of the core. And it turned out that the mixture of the flibe salt with lithium and beryllium optimized those two things. You don't have to have it, but you pay a neutronic penalty if you don't and a thermal hydraulic penalty if you don't. Companies today are looking at other fluoride-based salts that don't use lithium to avoid the tritium problem. And that's an example of these companies just doing risk mitigation. I'll pay the neutronics hit, but I don't have to mess with tritium. And so it sounds like a pretty good bet, right? But you can also sell tritium to folks. So if you think of it as a product, if you can get a handle on it, it's a potential revenue stream for you. So this shows a a layout of a demonstration reactor that was proposed for molten salts after the MSRE. This one, I think, is the MSBR, molten salt breeder reactor. And you can see there's the vessel, the pot. It has pumps up top and heat exchangers down here. It has multiple loops. It's a distributed loop system, and it has a drain tank down in the bottom. This was a calculation, I think, done by Ben Betzler to calculate the isotopics of a chloride fast reactor over an operational time. So these are all the isotopes that would be in a salt in this system. And when it's drained down to here, oh boy, that went a long way. How do we go back? My bad. When it drains down here, you'll have a huge dose in the lower regions of the plant. But when it's in the primary system in this calculation, I can calculate the flux to the surfaces and to potential equipment in this area. So this kind of shows the difference in the radiation environment of a molten salt reactor with a distributed source as opposed to one with a solid fuel in it. And so this becomes a design issue. You're not going to send a worker into that area to fix something if it breaks. So either it doesn't break or you have a way to repair it and replace it. So a big part of being economically successful with these systems is going to be develop remote technology for rad-hard environments that can go in and do inspection and maintenance, repair, and replacement. So that's a great problem to tackle as part of the development of these systems. So how do we get started with this? First of all, we make salts. It's like I tell people, if we were in the candy business, you'd expect us to be making candy every day. I mean, candy going out the door and selling that candy. So at the lab, we're trying to put in the capability to make salts consistently. But that's not good enough. You have to know what's in your salt. Mostly impurities are a big deal. Impurities drive corrosion rates in your system. So you must characterize salt. So salt production and characterization are investments that we have to make in order to do experiments that tell us how the salt behaves. So this is Melissa Rose from Argonne National Laboratory, and she is working with us on the chemistry. They are taking thermophysical property measurements of salts. We do it here at Oak Ridge as well. And the idea here is to make a bunch of salts and do round-robin testing to see how well we measure things and how consistently we make things. So this is one of the things that a university program could get involved with. We could send you salt. You could do a simple thermophysical property measurement and report your results and compare it to ours, and we'll see how well we're doing. So it's important to do that. Some things are difficult to measure, like specific heats of salt. You have to bring these up to high temperatures, maybe 1,000 C, in machines that are really not used to that. And the salt can be volatile, so things will start coming out of the salt. So you have to invent capability to measure the things that you want to have. And so this is an example of us developing a crucible for a DSC so that we can measure the heat capacity of salts. And it's a lot harder than you think to get good numbers. And trying to drive down the uncertainty on these measurements is a big part of our work. So we have people in the chemistry labs developing these devices using their machines to tell us that. This is a skimmer. It's a piece of equipment we put in. And basically what you do, you load up a salt sample about the size of a thimble. It's got a little hole in the top, and then you put it in a machine and heat it up. And then you look at what comes out the top. So you can measure the vapor pressure of chemical species and determine what they are as you heat up the salt. And this goes into our transport models so that if we have a salt, it's at a certain temperature, we know its composition, we know what's coming off of that and going to go into the off-gas system. We also know what's not coming out of the salt that's going to stay in there. So the skimmer is a new device. This is our lab. This is the lab where we make the fluoride salt over here in these glove boxes. So we can share with other programs and we can use it in our tests. This is a walk-in hood where we would put in a loop like a natural circulation, and it's vented to a HEPA system here as well. So we can make salt here, characterize salt here, and test salt here in this lab at Oak Ridge. And this is an example of what we do with salt. We got 316H exposed to a Flynac salt. It's a We use FlyNac as a surrogate because it doesn't have radiation material in it, doesn't have beryllium in it. It's easy to handle, but it behaves pretty well like fluoride. And we expose it to samples in both non-irradiation and in irradiation environments. And we look at how much corrosion occurs as a function of the purity of the salts. And the whole idea here is to figure out, well, how clean do I have to keep my salts before they start eating on my reactor components? I don't want to over-clean them because I'm losing money if I do so, but I don't want to get to a point where if I'm not paying attention, I've corroded a section of my machine and I can't fix it. So corrosion basic salt material interaction studies are a big part of our program. And again, back to the mass transport. That corrosion data can be used and put into a model so that we can predict on the plant level where we might see a problem in corrosion. And so think about it probably be in one of the hotter spots. It may be somewhere where flow velocities are increased. So you might go look at the inlet to a heat exchanger tube for potential corrosion. You can't look everywhere. Maybe you can develop a sensor that can detect when chromium comes out of your structural material and raise a flag if you see a concern. So we developed that technology to go with this knowledge to see if, one, can we predict where corrosion is going to occur, and can we detect it when it does occur, and how well can we do that so we can monitor the plant. Good old-fashioned experimental data. Just take some salt, put some graphite in the salt, and heat it up, and leave it there for a while and see what happens. Graphite is a porous material. You can get penetration of the salt into the pores. If you produce volatile fission products, xenon and krypton, maybe they can go into your graphite and make it radioactive, and then it becomes a waste disposal issue as well. So how these things interact is always an important part of the work, and I love modeling and simulation, but it's got to be anchored in data. So let's get the data, then we'll get the models, and we'll know where we are. So again, this is an example of chemical state modeling. If I take a salt at a certain temperature, it's all liquid and it's all gas at that temperature. But if it gets that much colder, this particular salt, not every salt, it can form particulates, and those can plug up pipes and tubes and things. So when you're operating, you're doing fine, but with this reactor concept, you have a minimum temperature that you have to start worrying about. You can't just turn it off and let it go cold, because you might form these solids and plug up your system, and it might be hard to get it back online. So these are the sort of things that are a little bit different when you have already a melted fuel that's distributed throughout your plant. So my activity is really focused on developing a framework to license these concepts. The reactor developers themselves, there's about 10 companies running around developing reactor concepts. They'll bring the design to the table. We'll help them analyze the designs and understand potential issues with those designs. But ultimately, if they're going to commercialize it, they're going to have to go through a licensing process, and there needs to be one put in place for that to happen. And basically what they're going to want to know is, does that reactor behave like you say it does, and what happens when things go bad? And that's usually translated as, what's the dose outside the plant? So that's why we worry so much about the mass accountancy for radionuclides and setting up a way to predict not only what we have in our system, but where it goes in the normal operation and off normal operation. If we can develop that, then we can follow the NRC and bring them along in the conversation with this new technology, so that in a few years from now, when we're ready to build our first one, they know what to look for, how to regulate it, what we're going to use that reactor to learn, and then how we're going to translate that into a commercial design that will go to the market with its fully qualified licensing in hand. So working with the NRC to get them to understand what we're doing, they've been very receptive, and have them tell us what we need to be thinking about so we can speak their language and meet their requirements is a big part of the conversation. So the NRC has been looking at advanced reactors for a number of years now, but now we're saying we want you to look at our specific advanced reactor, and ours is a little different. So we've got a big challenge in front of us, but they've been very helpful. All right. This is a plot of the load factor of reactor technologies as a function of time. I'm sorry, it's a little blurry, but 1982-ish, 2004. And what you see is a reactor that comes on the market. This blue line here is a pressurized water reactor. When they're running early in their life, early in their careers, they're usually lower, and we learn about them over time and bring them up to where they're operating consistently and reliably. But it takes a long time for any reactor technology to get to that mature level of understanding and operation. Okay? So remember, I don't have a lot of time to have something on the market to be available to replace light water reactors as they start to come offline. So this is where modeling and simulation, I hope, is going to help really pay off. We'll get the data to make sure we're using the right materials, and we'll predict the performance of the plants pretty well. But can we model and simulate a reactor with sufficient fidelity, including all major components, such that when we operate it for the first time, that it operates very well and requires very little modification to go online as a, I'm going to call near break-even option. I might not need to make a lot of money on my first reactor. I don't mind breaking even, that's okay. If we can model and simulate it before we ever operate it to have reliabilities that are good, then we can very quickly improve it to the next generation. And by that second generation reactor, you know, we'll have a moneymaker on our hands. Okay? So if you're a modeling and simulation person, remember that's really the point, to help us get onto good designs sooner that operate better. Okay? So a lot of issues come with trying to deploy a new fleet of reactors. Okay? Where are you going to get the fuel? How are you going to move it around the country? How many reactors do you think we need? We've got about 100 operating today, big ones. So we need 300 smaller ones to replace those, and 300 more smaller ones to increase our market share. So I need to deploy 600 reactors in this country if I'm going to make a difference on those items we talked about earlier. So bootstrapping that capability is part of the challenge. Just having a fuel cask that's good for this type of fuel will take years to develop. So there's a lot of good work to be done. All right? Getting a supply chain and industry together who can make these parts for us, these components, bootstrapping that's a challenge as well. And the use of reprocessing of materials and reuse of materials is kind of a new concept. We've been putting our used fuel in the dry cask storage and storing them. For salt reactor systems to work, we'd like to reuse that salt and put it in the next reactor and not have a waste product until we shut down that whole fleet. So these are challenges that we have to address if we can make that reactor, if we can make it work, and if we can make it economic. So MSRs are different, I give you that. They are a high-impact opportunity, and I think they can really revolutionize the nuclear business. And that's why I work on it, and I'm excited about it. They are demonstrated technology. The MSRE ran very well. We need to build more of these things and run them and test them. And I think we can have concepts that are commercially viable within a decade, maybe sooner. So with that, I will take any questions. I think you should prepare all reactor concepts to be base load, and that if you load follow, your economics can be better. Right? But I don't think that load following ought to necessarily be the driver that makes it commercially viable. I think it should be viable as a standalone, run full-time reactor concept. That's what I would aim for. But there are business models out there, and we'll let the developers decide what makes sense for them.
In your conclusions, was not really a conclusion because it didn't seem to me you talked that much about how can they be operational within a decade. So could you just, what are those companies and how close are they, and how much money is needed? Are we talking about 10 billion, 100 billion, a trillion, or?
So let's go back the other way.
Yeah, okay.
So there are about 10 companies that express interest in developing molten salt reactors. And the reason they're attracted to molten salt reactors is they think it's relatively simple technology that can be done at much lower cost. So that's kind of why they're picking this to get into the nuclear game. They already have designs that are derived from MSRE experience and some others, and those things are ready. The first demonstration reactor concepts are ready to be built. DOE has programs where we're trying to sponsor the construction and demonstration of advanced reactors, and we're hoping at least one of those will be a molten salt reactor, maybe two. That would be great. So these companies are talking about building their test demonstration reactors within the next 5 to 7 years. They don't have to invent any new materials. They can rely on demonstrated experience. So that's a very near-term initiative for them. Then you have to, of course, scale it up and have a commercial design that's economic. That'll be a little bit bigger challenge. But if you're successful with your demonstration reactor, there's a lot of investment dollars that can go into energy market. There's a ton of money out there for the next good idea. So if we can demonstrate we have a viable path forward, I don't think we'll have much trouble making it to the market.
Who's financing it? Are the PE money available, or is it Silicon Valley investors? Or?
Private investors are funding the industry partners to develop their concepts. And so there's a couple of operations that have a very significant amount of money and very influential people behind it. Those are further along. But there's also some very small companies that have some innovative ideas, but they hadn't caught on yet, and they don't have the big investors yet. But they're out there working on those. And if you have a good idea, you can find money, right? And that's what we're seeing out there. Now, we've seen some bad ideas, and they didn't find much money, and they've gone away. But that's the way a healthy market looks. We try something. If it doesn't work, we try something else. So I think we have a much more healthy approach to this than this monolithic, we're going to build one of these, and I hope it works.
But then there's DOE money.
DOE is investing heavily in advanced reactor development, and there's $200 million in the budget this year to potentially build 2 demonstration reactors. Hopefully one of those will be an MSR, and we'll get far along onto that first demonstration.
During this talk, you highlighted the importance of models. This might be a naive question because I think machine learning is a very catch-all thing that people just throw out there, and it may not have an application here. Do you envision that there's any room for using machine learning, probably not to replace physics-based models as a whole, but maybe supplement them in some cases where they may fail or not offer as, flexible an approach?
All right. I'm an old-fashioned guy. I came to school when we were still in the coal building, right? I remember that. So for me, if it doesn't work foundationally, we're not going to solve the problem by being clever, right? If we have foundational physics, then we have a chance. I see those concepts, things like integrated energy systems and AI, as being improvements over something that's already a good idea. So I'm not approaching it as that I need that to be successful. I think it's an enhancing capability that'll make me better later, but right now I'm just trying to put in the foundation. It's a good question. You can throw it. Yes.
For these companies that are looking at near-term, first-of-a-kind type deployment, what do you see as being the largest challenge that they face between now and then?
So again, it goes back to their technology choices, and these companies are doing things to mitigate risk. So if you're a company that's going to use fluoride-salt, then you may need enriched lithium. That could be your technical challenge. And your next challenge would then be, how do I manage and mitigate the tritium? But if you're a company that says, I'm going to just not do that, I'm going to take the hit neutronically and try something different, then you have a different problem. If you need high assay LEU, that could be a factor. And so the government is working on that so it can be made available for folks. So let's talk about just the specifics of these concepts. A molten salt pump that is highly reliable can run for 5 years without shutting down and having any maintenance, operate up to 800 degrees C is a huge technical challenge. It's not, you don't need to invent new things to do it, you just got to put the elbow grease in to do it. So getting the funding and the capability to develop the heat exchangers and the pumps are a big challenge for us. Thank you. You have to use the box.
So, since we have commercial liquid metal reactors and commercial gas-cooled reactors, why would there be a need for a demonstration liquid metal or gas-cooled? But we don't have commercial molten salt reactors, so it seemed like that should get emphasized. I guess that's been pointed out to DOE, but
You know, there's a lot of different takes on what we should do. And, you know, you have to learn that just because it's your thing doesn't mean it's everybody's thing, right? And so they take the opposite approach. Some people take the opposite view that, well, these are more mature, so they're closer to commercialization. Let's focus on them, okay? And so you're going to have to make the value proposition for your own technology and find your own support for it. And the more of that comes from external forces, the more leverage you have to make that case. So it's really going to come from the community, not going to come from internals. But
I guess the marketplace experience for the commercially available liquid metal reactors and gas-cooled reactors would suggest that perhaps the industry doesn't want it.
I love the free market. The free market will decide what's going to win, and let's step back and let it do its work. We'll be good. Have faith in America.